Assalamu alaikum. Hope you are doing fine. We have obtained the expression for electric field due to an infinite long charge carrying wire with the help of Gauss Law. In this video, we are going to get the expression for electric field for infinite long charged sheet using Gauss Law. For that, I consider this as an infinite long sheet carrying charge. Here it carries a positive charge. With the uniform surface charge density represented by letter sigma. This is sigma. This stands for surface charge density. Which is nothing but charge per unit area. Here when we say charge, it represents the charge enclosed by the closed surface. Okay. In order to get the electric field for this charged sheet, I apply Gauss law. We know very well, whenever we apply Gauss law to get the electric field for any charge or for any charged object, we take a closed surface. We call such a closed surface as Gaussian surface. Now in this case, suppose I have a sheet of this kind. Now from this sheet, the closed surface can be obtained by turning this into a shape of this kind. The shape that I have obtained is nothing but a cylinder. So I take a Gaussian surface in the form of a cylinder. And this cylindrical shaped Gaussian surface kept perpendicular to this plane sheet. Now I keep it this way. This is the Gaussian surface. Here I take one point here. I name this as point P. I take one more point here at this end. It is named as point P dash. This point P. I keep it. I write it inside. Point P. This point P dash. Then here, one thing I forgot to mention, the length of this cylindrical shaped Gaussian surface is a 2r on the side, r from here. So total distance, total length of this Gaussian cylinder is 2r and its area is E. This area is E. You remember this. Now, if I take any point at equal distance from this charged sheet, you will find the electric field. The magnitude of electric field remains the same. I repeat, points are taken at equal distance from this charge sheet provides the same magnitude for electric field. So, electric field is a constant here at some particular distance from this charged infinite long sheet. So, I read it here this way. E is equal to is a constant. Right. Then I will go ahead. Now, I will find out the value of E due to this charged sheet. For that, I will apply Gauss law. Now, before that, I write this. Phi E. Phi is nothing but electric flux, which is obtained by taking closed integral of the product of E vector and the dA vector. Here E vector is electric field and dA vector is the area of direction of the area element. Okay. Now, this can be expanded. This part can be expanded in this manner. Phi E is kept as such. Before I expand this, let me tell you something about this cylindrical shaped Gaussian surface. Here it has got three parts. This one part, this another part, and other one is a curved surface. Okay. Here is the curved surface. This is normal to this area element taken on the curved surface, and it provides us the direction of area element. Here dA is the area of this element that we have taken. Then, as this charge sheet comprises of positive charge, so the electric field projects outward in this direction. So, you can say the electric field is acting in this direction, and this is the direction of area element. Here, the angle between them is 90 degree. There is a 90 degree here. Theta is equal to 90 degree for this. Whereas here, when we talk about the point P and point P dash, here electric field act in this direction, and area element also have direction acting in the same way. So the angle between E and dA is 0 degree here, and the same thing for this side as well. Here this the direction of electric field, and this provides us the direction of area element, this part. So the angle here is 0 degree. Now these three parts comprises the closed surface. So I expand this manner. Line integral of E vector dot dA vector for curved surface. plus line integral of E vector dot dA vector for point P plus line integral of E vector dot dA vector for point P dash. We have these three parts which combinedly provides us the closed integral for this, and in turn it gives us electric flux. Now we know this. What do we know? We know that A vector dot B vector can be written as AB cos theta. So by following that method, now if I use this method here, then I can write E vector dot dA vector as E dot dA cos theta. So here E vector dot dA vector can be written as E dA cos theta. So in the place wherever I have E vector dot dA vector, I replace it with the E dA cos theta. What I do here? So 5E equals to integral of E dA cos theta. We know the value of theta here. For the curved surface, the theta value is 90 degree. The curved surface plus integral of E dA to point P cos of plus of P dash E dA cos of 0 degree. What I have written here is nothing but P dash. Okay. Now I am going to substitute the value of cos 90 and cos 0. We know cos of 90 is 0 and cos of 0 is 1. So when 0 is multiplied with this part, it becomes 0. So what do I get in the next step? Is this 5E equals to 0 plus integral of E dA into 1 here P plus integral of E dA into 1 here P dash. Got it. Now this can be written here in this way. We know, what do we know? We know that E is a constant. When we integrate a constant, we can't integrate a constant, so it is taken outside. So here E is the constant, so it is taken outside the integration. The next step, this can be written here in this way. 5E equals to E integral of dA plus E integral of dA. Now if you want, you can mention P. Otherwise, even if you leave this, it is not going to make any big difference. Okay, this is what we have got. Then in the next step, we'll see how I write this. I write it in this manner. 5E is written as E. Now when I integrate this term, now let me show you a simple formula used in integration. Integral of dx is x. The similar way, integral of dA is a. Integral of dA is a. Right here. Integral of dA is a plus EA again. So, for your understanding, I write it here. Integral of dA is in the similar way. Okay, I got this. Now, when EA gets added with another EA, what do I obtain is nothing but this. 5E becomes equal to 2EA. This is the expression for electric flux. Now I will apply Gauss law. What is Gauss law? Gauss law. Gauss law relates the electric flux. So 5E is equal to charge upon epsilon naught. Here charge is the charge enclosed by the Gaussian surface. So enclosed charge divided by epsilon naught. Epsilon naught is nothing but permittivity of free space. You remember that. And about this we have learned at the beginning of this chapter. So here, this is what we have obtained. Now in the place of 5E, I am going to write this. Okay. Or we can also do the reverse thing. In the place of 5E, I can write this value. If I do so, what I obtain? See, in place of 5E, I write this. So I get 2EA, okay, in the place of this one, is equal to enclosed charge divided by epsilon naught. What is my aim? My aim is to get the value of E. So just by cross multiplication, this can be obtained very easily. So see what I do? I keep E this side and remaining terms are taken that side. So equals to 1 by 2A. Here 2A is multiplying. When it is taken to the other side, it will divide. You will go to the denominator. Then into enclosed charge divided by epsilon naught. Now here, if you remember, we have written this expression at the beginning of this topic. Here sigma. Sigma is nothing but surface charge density. What is sigma? Sigma is surface charge density. This symbol is known as sigma. Surface charge density is equal to enclosed charge upon area. So from this, enclosed charge can be obtained by cross multiplication. If you multiply sigma with A, you get a enclosed charge. So I box this to make our work easy. So in the place of enclosed charge, I am going to use this. Here, in the place of this, I will use this expression. So what I will get? I get this. E equals to 1 upon 2A equals to sigma A from here divided by epsilon naught. This is what we are taking. I box this. Then, if you look at this carefully, I rewrite this one here as such. E is equal to 1 by 2A into sigma A upon epsilon naught. Here, this A, this will get cancelled, and what do we obtain is something but this. E equals to sigma upon 2 epsilon naught. This is the final expression that provides us the electric field due to an infinite long charge carrying plane sheet. So E is equal to sigma upon 2 epsilon naught is the electric field due to this charged sheet. And if this is completely plain, if I take a point, if I take a large number of points at equal distance from this charged sheet, then at all those points, the magnitude of electric field is going to remain same. Okay? If it is not the plane, then the magnitude of electric field at points taken at equal distance is going to differ. You remember that. Okay. Then let me provide some more information about this. Here we have taken a positive charge. That means for positive charge, sigma is a positive, or we can write it like this: sigma is a greater than 0. Okay, when a sigma is greater than 0, then electric field lines will be projecting outward. You will be projecting outward. You remember that. So E projects outward. Right? And for negative charges, negative charge, sigma takes the value as minus sigma, and here sigma is lesser than 0. So in this case, E acts inward, So if the charge sheet is provided with a negative charge, then the electric field will be acting towards it. Now this is known to us already. Now we have learned about it. Suppose we have a positive charge. Because a positive charge, the electric field lines are projecting outwards. This is arrow mark represents the direction of electric field. They project outward. Now, I add a few more lines here. Here, the electric field is acting outward. Whereas when we have negative charge, suppose we have a negative charge in the place of this. When we have negative charge, then the electric field lines are acting towards it. So that is why we have plus sigma for positive charge and minus sigma for negative charge. In case of negative charge, electric field is acting inwards. For positive charge, electric field acting outward. You remember this. So this is the final expression. Now I will show you what happened to the electric field when we have taken two charged plane sheets carrying different charges. Before that, let me tell you how to write this expression in vector form. In vector form, this is written as E vector equals to sigma upon 2 epsilon naught. Here, a small thing we include here. That's nothing but n cap. And n cap is the unit vector which provides the direction to this part. So I box this. Now let me show you what happens to the electric field when we take two plane charged sheets carrying different charges. For that I consider two plane sheets. This is one plane sheet and this one is another plane sheet. of them have the same area and kept parallel to each other. This sheet carry positive charge. So the surface charge density of this sheet is plus sigma, whereas this sheet have a negative charge. So its charge density is minus sigma. Now I select 3 points, point P1, point P2 and point P3. If you look at these 3 points, find the point P1 is lying between the parallel plates, whereas point 2 and point 3 are lying outside the charged sheets. Now, what will be the electric field due to these 2 charged sheets acting at point P1 that I am going to show you? We know very well, if we have a positive charge and a negative charge, then in such case, the electric field lines starts on positive charge and ends at a negative charge. This we have learned earlier. So in that way, the electric field is acting away from the positive charge and towards the negative charge. So here, the electric field due to this positively charged sheet is acting away from it. It is represented as E plus vector, and the electric field due to this negatively charged sheet is acting towards it, which is represented as E minus vector. Due to positive charge, it acts away. Due to negative charge, electric field acts towards it. So these 2 electric fields are acting in the same direction. Whereas here, the electric field due to the negative charge is acting towards it, and the electric field due to positive charge, positively charged sheet is acting away from it. So E minus vector, this is E plus vector. So that is the opposite direction. So they cancel each other. And in this case, the electric field due to positively charged sheet is acting away from it, E plus vector, and the electric field due to negatively charged sheet at this point is acting towards the sheet, is E minus vector. So they act in the opposite direction, they get cancelled, and the resultant electric field here is 0, and here also it is a 0, whereas here both the electric fields are acting in the same direction, so they get added up. We know the expression for electric field due to a charged sheet is nothing but sigma upon 2 epsilon naught. So here total electric field is obtained due to this. E plus the E minus. So the value is, from this expression, sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught. This is the total electric field, and as written here in this manner. E vector is equal to half and half becomes 1, sigma upon epsilon naught. This is the electric field present at point P1 due to these 2 charged sheets carrying different charges, and at point P2 and P3 the electric field is 0. Instead of ER you can also take it as just E. The same here as well. So E vector is 0 here, here also it is 0. So from this we understand that there is no electric field lie at a point outside the two parallel charged sheets, whereas the electric field is present between these two parallel charged sheets. I hope the video is useful. If you have any kind of doubt related to the topic, can you put your questions in the comment section. Thanks for watching.